Hello, welcome to GP Podcast. Today, we're going to pull back the curtain on a piece of technology so incredibly advanced, it really does feel like something straight out of science fiction. We're talking about a machine that quite literally builds our modern world, one atom at a time.
So let's just jump right into the big question. Think about any device you're using right now. Inside it, there are microchips, and those chips are crammed with billions of transistors. But here's the kicker. The real challenge isn't just how many there are. It's how ridiculously small they are. We're talking about features that are almost, well, unimaginably tiny. So how on earth do you mass produce something you can't even see? And not just produce it, but do it millions of times perfectly every single time. The scale we're dealing with here is just mind-boggling. We're talking about 10 nanometers. Now, to give you some perspective on that, a single human hair, that's about 80,000 nanometers wide. So yeah, we're operating on a level that's honestly hard for our brains to even wrap around. Yeah, you heard that right. We're building the fundamental circuits of our world with components that are only about 45 silicon atoms across. I mean, just think about that for a second. To actually build something that small and do it reliably over and over again for millions of chips, you need a machine that is, for all intents and purposes, impossible. So, how do they solve this impossible problem? Well, the answer is a process with a fancy name, photolithography. But don't let the name scare you. The easiest way to think about it is like a nanoscale photocopier, but a photocopier with a level of precision that is just absolutely staggering. The real magic here, the key to the whole thing, is that we're using light. Light itself is the tool. It's used to transfer an unbelievably detailed pattern, think of it like a stencil, onto a silicon wafer. And that wafer, that's the foundation for every single microchip we use. And the process itself is, at its heart, a kind of beautiful three-step dance. First, you take that silicone wafer and you coat it with this special light-sensitive material. Then, you shine a very precisely patterned beam of light onto it. And finally, you develop it. You basically wash away all the parts that were hit by the light, and what's left behind is a perfect, microscopic stencil all ready for the next layer of the chip to be built on top. And just to give you an idea of the sheer density of information we're talking about, it's just insane. I mean, forget circuits for a minute. If we were printing words on a single layer of just one chip, you could fit all 7 Harry Potter books, plus the entire text of the English Wikipedia, and you'd still have enough room left over for every single book in your local public library. That's how much detail we're talking about. And this machine copies all of that in under a second. Wild. Okay, but here's the next big hurdle. If you want to draw lines that are only a few atoms wide, you can't just use any old light. It's kind of like trying to do incredibly detailed artwork with a fat magic marker. It's just not going to work. You need a super, super fine-tipped pen. In this case, that means light with an incredibly short wavelength, just 13 nanometers. So, where do you get this special 13 nanometer light? Well, that's the thing. This kind of light, it's called extreme ultraviolet, or EUV for short. It just doesn't exist naturally here on Earth. You can't bottle it, you can't find it, there's no switch you can flip. If you want it, you have to make it. And this is where the engineering just goes to a whole other level. It's absolutely mind-bending. Because this light doesn't exist, the machine itself has to forge it, right there on the spot. It has to create it, on demand, inside a vacuum chamber, using a process that is a crazy combination of incredible violence and pinpoint precision. Check this out. At a rate that is just dizzying to think about, the machine fires these tiny, tiny droplets of molten tin into a vacuum chamber. And I mean tiny. Each one is smaller than a grain of sand. And it does this 50,000 times a second. Okay, so you've got this stream of tiny tin droplets flying through the chamber. And as each one passes, it gets zapped by an immensely powerful laser. And when I say powerful, I mean it. We're talking about a 25 kilowatt laser beam. That's more than 10 times more powerful than the kind of industrial laser they use to cut through solid steel. So this monster laser blast slams into the little tin droplet and just vaporizes it. Instantly, it creates this tiny, brilliant flash of glowing plasma that's actually hotter than the surface of the sun. And right in that one fleeting microscopic moment, that plasma shoots out the exact 13 nanometer wavelength of EUV light they need. It's literally forging a tiny star, on demand, 50,000 times a second. All right, so we've done it. We've forged starlight inside a machine. Awesome. But of course, that just leads us to the next impossible problem. This EUV light is so high energy, it's so aggressive, that it gets absorbed by pretty much everything it touches. And I mean everything, even air. That's right. Just the molecules in the air would stop this light in its tracks. So what does that mean? It means the entire path the light travels has to be a hard vacuum, as close to perfectly empty space as we can get. The inside of this machine is basically its own self-contained universe, totally sealed off from our atmosphere. And get this, you can't even use normal mirrors. A regular mirror would just soak up the EUV light like a sponge. So they had to invent the most perfect, most complex mirrors ever created by humans. But even these incredible mirrors, they're not perfect. Each one still absorbs about 30% of the light that hits it. So after that precious, hard-won starlight bounces through a whole labyrinth of these mirrors to get where it needs to go, less than 10% of it actually makes it to the silicon wafer. And that brings us to the final, and maybe the most insane, challenge of all: precision. See, you're not just making one stencil, you're building a chip layer by layer painstakingly. And that means each new layer has to line up with the one before it perfectly. If you're off by the tiniest fraction, every single chip on that wafer is trash. Gone. The whole guiding philosophy behind this machine can be summed up in a Dutch phrase: meten is weten. It means to measure is to know. And it's not just a saying, it's a fanatical obsession. Every single variable you can possibly think of, the tiniest change in temperature, the slightest vibration, the exact position of everything, it's all measured constantly and compensated for in real time with just absolute mind-numbing accuracy. So you have this stage that holds the silicon wafer, and it has to move in perfect lockstep with the mask holding the blueprint. So how perfect is perfect? Well, the accuracy they need to maintain while everything is moving is less than a single nanometer. Just let that sink in for a moment. This machine is moving and positioning an object the size of a dinner plate with an accuracy that is smaller than the width of just 4 silicon atoms. This isn't just engineering anymore. It's a perfectly choreographed subatomic ballet, and it happens hundreds of times, flawlessly, on every single wafer that goes through it. So from forging starlight inside a vacuum to directing a flawless subatomic dance, this impossible machine is really the silent hero behind our entire digital world. It is, without a doubt, one of the pinnacles of human ingenuity, and it's busy building our present right now as we speak. Which really makes you wonder, right? What kind of future will its successor build? If you liked the video, subscribe, leave a like, comment on what you liked most, and share the video. Your support really helps us create more explainers just like this one. Thanks for watching.